Welcome. In this screencast, we look at how to find areas enclosed by polar curves. So the main idea here is that you have some polar curve. Maybe it looks like this, and you're looking at the area from theta equals alpha to theta equals beta, and you're trying to find this area for some curve R. It's a function of theta. How the heck do we do that? Well, in Calc 1, when we tried to find areas in a rectangular system, we worked from left to right, and we made these rectangles. Then we found the areas under the rectangles, and then we made the rectangles thinner and thinner and thinner, and it became a Riemann sum. But that's not how this goes. Theta equals alpha is on a slant, theta equals beta is in a slant, and we're looking to fill in this area in between them. So how does this really go? Well, we break it up into a bunch of sectors because we know how to find the areas of circular sectors, right? That's one thing we know how to do. So when we go to find the area, it's approximately a sum of n different sectors, and we find the area of a sector by taking 1/2 times the radius of the sector squared times the angle between the rays, and that's some change in theta. That's what we do in polar coordinates. We don't use rectangles because we're not in rectangular coordinates. We use sectors because we're in polar coordinates. And then I think you know where this goes. You make them thinner and thinner so that there are more and more sectors, and you let n go to infinity. And in the limiting process, the area becomes an integral from alpha to beta of 1/2 r squared, and then the delta theta becomes a d theta, as you are familiar with from your Calc 1. So this is how we find area bounded by a polar curve. So find the area enclosed by r equals 4 cosine 2 theta. 4 cosine 2 theta. That's this rose curve. That's this rose curve. 4 leaves, each of which are symmetric about either the x-axis or the y-axis. And so I propose that we look at theta equals pi over 4 and theta equals 0 and find this area and then multiply by 8. Because there are 4 leaves and this is half of a leaf, and we know it's half of a leaf because we can take 0 to 2 pi and break it up into 8 little regions. So the area is 8 times the area of this part of this leaf. And that runs from 0 to pi over 4, and it's 1/2 r squared d theta. And if we can do that, we win. So 4 squared is 16, times 1/2 is 8, times 8 more is 64. And here's the hard part. How do we do that? How do we do the integral of cosine squared of something? Well, that's from a lesson gone long ago where you were like, gosh, I hope we never have to do this integral ever in a million years. But it turns out that we use the double angle formula to get an equivalent expression in terms of the double angle. Twice 2 theta is 4 theta. But we can find this integral. This is not bad at all. Antiderivative of 1/2 is 1/2 theta. Antiderivative of 1/2 cosine 4 theta is 1/8 sine of 4 theta. We evaluate between 0 and pi over 4, and I won't bore you with details. So this was a scenario where we set up the integral 1/2 r squared d theta from here to there, and then we used an integral technique from previously in our course to take an antiderivative and be done. One other, just to mess with us a little bit, find the area inside r equals 4 plus 4 cosine theta, but outside r equals 6. Inside of this, where this goes all the way out to 8 on the x-axis, but outside of this, r equals 6 is a circle. This is r equals 6. This is r equals 4 plus 4 cosine theta. We're looking for this area. Really, we're looking for twice that area, but we'll find this area and double it. We will double the area that we're interested in here. This is theta equals 0. This is theta equals pi over 3. How do I know that? Because we can set this equal to that, and using high school trigonometry, we can figure out that those are equal when theta equals pi over 3. So we're going to integrate between 0 and pi over 3. What are we going to integrate between 0 and pi over 3? Well, in Calc 1, we would have done top curve minus bottom curve, but that's not what we're going to do here. We're going to find the red area and subtract out the blue area. Well, what's the red area? The red area is 1/2 r squared d theta. What's the blue area? The blue area is 1/2 r squared d theta. So we take the red area because that's outside. We take the blue area because that's inside. And we do red area minus blue area. Well, it turns out after some work and a double angle formula that this is 32 sine theta plus 8 theta plus 4 sine of 2 theta from 0 to pi over 3, and that's 18 radical 3 minus 4 pi. That's what this is. So what's more important is the setup, because you're calculator active in all likelihood on this question. What's more important is the setup. When we're looking for an area between two polar curves, we take the outside area and subtract the inside area. The outside area is all of this, and the inside area is all of this. 1/2 r squared, 1/2 r squared, and we subtract. Hope that this is helpful to you.